Water boils at 100 degrees, but can we do it at 20 degrees Celsius? Welcome to Teclen Lyophilization Knowledge Hub. In this first video, we are going to be talking about water sublimation at low pressures. Vacuum phase changes depends on pressure. While water boils at 100 degrees at atmospheric pressure, it boils at 120 degrees in a pressure cooker. And hikers at the top of the mountain, they experience low temperature boiling at 90 degrees because of the low atmospheric pressure. So boiling temperature depends on pressure. When the pressure is high, the boiling temperature is increased, and when the pressure is low, boiling temperature is decreased. But we can reduce enough the pressure to make water boil at 20 degrees. Let's see the following video. We can see how a glass of water is introduced inside the chamber of a fridge dryer, that a probe is inserted in it, and then we close the door. Then a vacuum pump is evacuating the air inside the chamber, producing vacuum. Nothing happens from 1000 millibar to 30 millibar. But then bubbles start to form. This is because we have reached the boiling pressure at 20 degrees. But not only that, we can see that the boiling process is causing the temperature going down up to a point 0 degrees, when we can see that the water freezes and continues going down until temperature and pressure reaches an equilibrium. So what just has happened? What cooled down the liquid that at the end it freezes? Because the fridge dryer shelf is at room temperature. The glass containing the water is at room temperature. The vacuum chamber walls are at room temperature. To be honest, it took me a lot of time to understand this phenomenon. Even when I'm doing this experiment with expert scientists, biologists, chemists, pharmacists, everybody gets really surprised. And barely nobody can answer me the question, what is cooling down this water? So I am going to give you some seconds now, so you are able to think. You can stop if you want the video, and then I will give you the answer. Are you ready? The plain answer would be that in order that some liquid can become vapor, some energy needs to be provided. And the only one that can provide this energy is the remaining liquid. So in other words, the heat to produce the boiling is provided by the remaining liquid. In order to provide you with a better explanation, I am sorry, but I need to go to the physics of this phenomenon. So here you can see a phase diagram, pressure, temperature. The pressure is in millibar and the temperature is in degrees Celsius. And here we have three green lines that are separating three areas for stable ice, stable liquid, and then stable vapor. At 1000 millibar atmospheric pressure, liquid freezes at 0 degrees and water boils at 100 degrees. And as we were explaining at the beginning of the video, if we increase the pressure, the boiling temperature increases. If we reduce the pressure, the boiling temperature is reduced. But what happens if we start at 20 degrees with liquid water and then we suddenly reduce the pressure down to, for example, 1 millibar? Here, water cannot be longer in a stable state in liquid form. It needs to be vapor. So in order that some part of the liquid can be vapor, part of this water needs to reduce its internal energy, being cooled down, until it reaches the ice area. So part of the original water becomes ice and part becomes vapor. Fortunately for us, the freeze drying process is not that complicated. From a pharmaceutical dissolution originally at 20 degrees, what we are doing is cooling down to freeze it, for example at minus 40 degrees in a freezing step. Then we reduce the pressure, vacuum, for example to 0.05 millibar, to then heat again. But when we are heating, we are crossing the sublimation curve, going directly from ice to vapor. and then the pharmaceutical product is dry. In pharmaceutical freeze drying, pressure is precisely controlled to then, by an accurate heating, being able to freeze dry the product within the allowed temperature margin. From Teclen, we provide the necessary containers for an enhanced performance. As it can be seen in our stainless steel cup with a perfect flatness and finish for a good contact with the freeze dryer shelf. Also, a really good adjustment of the membrane with the threaded ring allows a freeze drying process with no fly out and no contamination without compromising the performance of the cycle. If you want to learn more about how to freeze dry pharmaceuticals and how Teclen can provide you with the essential tools for it, please do not miss the second video of this series of videos of the Teclen lyophilization knowledge.